Hello, geometry people. So today we are going to be looking at the converse of proving two lines are parallel once you have one of our corresponding, alternate interior, alternate exterior, congruent. So remember that the converse of a statement, if you're given P implies Q, is Q implies P. So the idea behind this is anytime the conclusion is you have parallel lines, that's going to be a converse. So for instance, we don't know anything about J and K over here. But if I know that angle 2 and angle 6 are congruent, so if my corresponding angles are congruent, then I can conclude I have parallel lines. So notice it is the reverse of what we had yet last time, where if you had parallel lines, you knew the corresponding angles are congruent. So I call this the converse of your corresponding angle theorem. It's the easiest way to write it. So if we want to prove that two lines are parallel, we want to make the two angles, in this case our corresponding angles, we want to make them equal. So let's solve for x by setting 3x plus 5 equal to 65. So 3x equals 60. So if x is 20, then those two angles are congruent and the two lines would then be parallel. Over here, if you don't have a specific relationship, you can kind of jump around. We know that if this is 75, this has to be 75 if those angles are parallel. And then 75 and 105 are supplementary. So because that all works, we know that M is parallel to N because the corresponding angles are congruent. And then we also here have the same for alternate interior. So now if you know your alternate interior are congruent, so if your alternate interior angles are congruent, then we know we have parallel lines. So the conclusion is about the parallel lines. All right, so we're going to prove this theorem. And like every theorem, we cannot use the theorem in the proof of the theorem. So we start off with our given. So we are given angle 4 is congruent to angle 5. That was given to us. And so we need a couple other relationships so that we can get to our parallel lines. So let's see. Notice that we have angle 1 is congruent to angle 4. So think about why that is. So we have angle 1, angle 4. It's because they are vertical angles. And if 4 equals 5 and 1 equals 4, then that means angle 1 equals angle 5, or is congruent to angle 5. That's just substitution. So this is how most of these work. You will set up a couple relationships, and then by substitution, you'll get either your alternate interior, your corresponding, or your alternate exterior congruent by substitution. Now that I have what I know to be corresponding angles as congruent, I can conclude that the two lines must be parallel. That is the converse of the corresponding angle theorem, because that's the relationship that came right before the parallel lines. But we started with a given about alternate interior angles. So we just proved that if the alternate interior angles are congruent, you know the lines will be parallel. Okay, so let's keep going. This one, notice here we have our alternate exterior, and they are marked as congruent. So if your alternate exterior angles are congruent, then we know we have parallel lines. And again, I would abbreviate this one. So I should have written this a little smaller. Converse of the AEA theorem. And I guess I should have written that above up here. I would label this the converse of the AIA theorem. There we go. And our last one is consecutive interior. Now remember, consecutive interior have to be supplementary. So the way this one will read is if my CIA are supplementary, then I know I have parallel lines. And I would abbreviate that. I don't have a lot of room there, so I'm going to just write it down here. That would be the converse of the CIA theorem. All right. So let's play around with this. Now we want to find the value of x that makes the lines parallel. So once again, these are corresponding angles, so we know they should be congruent. So we set them equal to each other. Subtract 55 from both sides, and we get that x. So if x is 5, those lines will be parallel. And over here we have alternate exterior angles, which should be congruent. 200 minus 2x equals 130. So I'm going to subtract 130 from both sides and add 2x to the other side, so then x will equal 35. Okay? All right, so then we have here, now you have to be careful with these ones because I strongly recommend like colored pencils. I know that was a little thick, wasn't it? I know these two lines are going to be parallel. And so in reality, if I'm going to use those parallel lines, I can only make any comments about angles from here and here along the transversal that those two parallel lines share. So we have in the diagram R is parallel to S, angle 1 is congruent to angle 3, and we want to find out, is P parallel to Q? So let's kind of do this as if it was a proof. So we're given that R is parallel to S. That was given to us. So from that, if those two lines are parallel, notice that angle 1 and angle 2, those are corresponding angles. So by the corresponding angle theorem, I know those are congruent because they're coming off, they run along a transversal right here. So angle 1 and angle 2 are congruent, but we were also given that angle 1 is congruent to angle 3. That was also given to us. So by substitution, I know that 2 is congruent to angle 3. So that would be your substitution. Sorry, I'm running out of space there. And if 2 is congruent to 3, well, what relationship is that to P and Q? That makes those alternate interior angles. So we know that P now is parallel to Q by the converse of the AIA theorem. So again, anytime your conclusion is that you have parallel lines, you're going to use a converse. If your conclusion is that the angles are congruent or the angles are supplementary, that will be your direct corresponding alternate interior, alternate exterior, CIA supplementary, one of those theorems. All right? And then we have this concept of the transitive property for parallel lines. So remember, transitive property says that if A equals B and B equals C, I can cut out the middleman and A equals C. Well, you can do the same thing with parallel lines. If P is parallel to Q and Q is parallel to R, well, then it kind of makes sense that you can then conclude, cut out the middleman, P will be parallel to R. Okay? So it's a nice little theorem, but it kind of makes sense too. All right. Now we're going to decide whether there's enough information to prove that M is parallel to N. So in part A, what do you think? Take a look at it for a minute. If you want, you can pause the video, but I will then keep going. So you're given these two angles are congruent, and those with respect to M and N are corresponding angles. So we know that M is parallel to N by the converse of the corresponding angle theorem. In example B, you are given vertical angles, but nothing down here, so there's no conclusion. We don't have any alternate interior corresponding any of our relationships on that one. And here, since what we're trying to figure out is M parallel to N, we can really pretty much just ignore S. So these two angles that are marked as congruent are alternate exterior. So we know M is parallel to N by the converse of your AEA theorem. So I have it written on the board for you, but again, when you are concluding, if your concluding about angles, then you're going to use either the corresponding, alternate interior, alternate exterior, or the CIA. And if you're concluding about parallel lines, then you're going to use the converse of each of those above. Converse of the corresponding angle, the converse of the AIA theorem, the converse of the AEA theorem, and the converse of the CIA theorem when your conclusion is about parallel lines. All right, now I realize number 3 on your CFU is going to be a difficult system of equations. So if you want to hold off on that one, I can help you with it when I return to class. Otherwise, go ahead, good luck, and I will see you guys next time.